We're ready whenever you are.
Okay, Bernhard, are you all set?
Yes.
Okay, super. Okay, so welcome everyone to a series of 3 seminar talks in the context of the Rothschild Fellowship by Bernhard Keller. So the first talk will be today, and then there will be another talk next Wednesday, the 13th, and the following Wednesday, the 20th October. But please note that next week and the week after, the start time will be 1 hour later. So it will start at 3 p.m. UK time. Great. It's my pleasure to announce a lecture by Bernhard Keller on cluster algebras with coefficients and relative cluster categories.
Thank you very much. Yes, so I would like to speak on cluster algebras with coefficients, and I have slightly changed the title. So now it's Higgs categories instead of relative cluster categories, because the role of the Frobenius category is really played by the Higgs category, not the relative cluster category. But we will see that in detail. And this is mostly after Yilin Wu's recent PhD thesis, and I will work over an algebraically closed field of characteristic 0, which I will denote by C. And let us look at an ice quiver. So remember that's a quiver which is finite, without loops nor 2 cycles, and endowed with a frozen subquiver. Here we have examples. As here a very simple example with just one frozen and one non-frozen vertex. This is a typical, very small example from Geiss-Leclerc-Schroeer's theory. And this is an example from the study of Grassmannians. And associated with such an ice quiver, we have a cluster algebra. And I write this little plus to mean that it is a cluster algebra with non-invertible coefficients. So the coefficients form a polynomial algebra. And this is associated with the ice quiver. The vertices, the frozen vertices, are in bijection with the initial coefficients, with the coefficients. Okay, and well, it's important to look at cluster algebras with coefficients for several reasons. The main one is probably because they describe coordinate algebras on important varieties. For this example, the variety is a maximal unipotent subgroup in SL3C. And for this example, it describes the cone over the Plücker embedding of the Grassmannian of planes in 4-dimensional space. Okay, now for categorifying such cluster algebras with coefficients, 2 main methods are known. So the first one is based on the cluster category. So we just take our quiver Q and for the moment forget about the coefficients. We choose a non-degenerate potential on our quiver Q. And then inside this cluster category, we have a canonical cluster tilting object, namely the image of the Ginzburg algebra. Yes, this is constructed as a quotient of the perfect derived category of the corresponding Ginzburg algebra. And the free model of rank 1 over the Ginzburg algebra gives us this canonical cluster tilting object. And so this in principle categorifies the whole quiver. And now we simply disallow ourselves to mutate at non-frozen summands. So the non-frozen summands are those with, we disallow to mutate at frozen summands. We only allow mutations at non-frozen summands. And well, this method works, and it works for arbitrary ice quivers. So that's quite nice. But on the other hand, in the examples arising in nature, as you can see here, there are natural arrows between frozen vertices, and these arrows are not taken into account correctly by this type of categorification. And so there's another type of categorification which does take the arrows between frozen vertices into account. That's via Frobenius categories. So we take a stably two-color Frobenius category, and we suppose that we have a cluster tilting object, so that the associated ice quiver, yes, so we take the quiver of the endomorphism algebra, yes, we suppose that that makes sense. For example, the category is homofinite, or this algebra is pseudo-compact. Then we have a well-defined quiver associated with the endomorphism algebra, and we suppose that it's isomorphic to Q in such a way that the projective, injective factors of T correspond to the frozen vertices in Q. Okay. Now, this second method does not work, for example, for this very simple example. Yes, it cannot work. Yes, in this example, this corresponds to the unique indecomposable projective injective object. And this is a non-projective object. And since we're in a Frobenius category, of course, we need an inflation from this object to some injective object. Yes, but this cannot exist because in this category, hom from 2 to 1 simply vanishes. So we cannot have such an inflation. And in general, this second method never works for principal coefficients. You can find the detailed argument in proposition 2.3 of Matthew Preston's preprint from February 2017. Okay, so this is the disadvantage of this method. It is restricted to certain classes. On the other hand, the advantage is that it correctly takes into account the arrows between frozen vertices. And the arrows between frozen vertices are important for at least two reasons. Yes, you use these arrows when you glue ice quivers, and that is an important construction. You can see it, for example, in recent work by Merlin Guest, and you can also see it in Foucault-Charov's amalgamation construction. So here you definitely need them, and then you also need them in the recently introduced mutation at frozen vertices. Chris Fraser and Melissa Sherman-Bennett introduced this operation, this mutation at frozen vertices, in their study of cluster structures on positoroid varieties, and it is a very useful tool. And it definitely needs the arrows between frozen vertices. Okay, so now the aim of this mini course is to describe Higgs categorification, which has the advantages of Frobenius categorification. It takes into account the arrows between frozen vertices, but it works in much greater generality. Ultimately, it should work in complete generality, like the Amiot construction. For the moment, we have done it for the relative Jacobi finite case. I will say what that means in a second. And that's also already a nice class. Okay, so now let me denote by a Q without the plus the cluster algebra with invertible coefficients. So this here, the coefficients, it's an algebra over the Laurent polynomial algebra in the coefficients. It's associated to our ice quiver. So this is one object I need. Then secondly, I need the reduction of the ice quiver, Q bar. It's obtained by removing the frozen vertices and all the arrows incident with the frozen vertices. Okay, now let's take a non-degenerate potential on our quiver, and we assume that the associated relative Jacobian algebra is finite dimensional. So the relative Jacobian algebra is defined in the same way as the usual Jacobian algebra, only we take the cyclic derivatives only with respect to non-frozen arrows. So we take the completed path algebra and we divide by the closed ideal, closed two-sided ideal generated by all cyclic derivatives with respect to the non-frozen arrows. So we suppose that this is finite dimensional. So of course in the first example we can just take W equal to 0. In the second example we can take W A B C. And in the third example I think there is no such W, yes, but at least there is no obvious one. Yes, the obvious one gives an infinite dimensional relative Jacobian algebra. Okay, and then now with these notations I can state I can give you the list of main objects and what they correspond to in the classical case. So, well, here we have our cluster algebra with non-invertible coefficients. And it corresponds to the Frobenius category in Frobenius categorification. And in Higgs categorification, it will correspond to the Higgs category. So this category E is a Frobenius exact category. And this Higgs category is only a Frobenius X triangulated category. So if the set of frozen vertices is empty, then this will specialize to the usual cluster category. On the other hand, well, in this case, for example, it will specialize to the module category of the pre-projective algebra, yes, which is the Frobenius category used to categorify this example. Yes, so it is something which can be a Frobenius category, but it can also be a triangulated category. In general, it's a Frobenius X triangulated category, and we can use it to categorify the cluster algebra with non-invertible coefficients. So it is associated with each ice quiver satisfying this finiteness condition. And yes, indeed, well, it can be defined in greater generality, but we haven't yet had the time to study its properties in greater generality. Okay, and then, well, from the cluster algebra with non-invertible coefficients embeds into the cluster algebra with invertible coefficients. We just localize with respect to the coefficients. And I claim that a nice categorical lift of this embedding is the passage from the Frobenius exact category to its derived category. So we pass from a Frobenius category to a triangulated category. Yes, so I will in the second part of the lecture I will try to convince you that this is a reasonable categorification of this localization with respect to the coefficients. And here in the Higgs categorification, well, the Higgs category embeds into the relative cluster category. So the relative cluster category is the generalized version of the bounded derived category of our Frobenius category, and in certain classes of examples, it is equivalent to the bounded derived category of the Frobenius category. And then we have a third level. Yes, we can here, this is the cluster algebra with invertible coefficients. We can specialize the coefficients. Yes, so that's the specialization of the coefficients to 1. Then we get, well, a usual cluster algebra without coefficients associated with this reduced quiver. And this passage then corresponds to the canonical functor from the derived category of the Frobenius category to the stable category. And here as well, if we compose this, then this will identify with the stable category of this Frobenius X triangulated category. And it is also the usual cluster category associated with the reduced quiver and the reduced potential. So here we have the three diagrams. Yes, here we have, yes, sorry, this is not the wrong notation, so I didn't include this F in the notation. Yes, so here we have the cluster algebra with non-invertible coefficients. Then we can localize it to get a cluster algebra with invertible coefficients. Then we can pass to the specialization of the coefficients to 1. From here, from the Frobenius category, we can pass to its derived category and then to its stable category. And we have the same at the level of the Higgs category. The Higgs category embeds into the relative cluster category of our ice quiver with potential. And we have a canonical quotient functor to this category, the cluster category of the reduced quiver with the reduced potential, and that also identifies with the stable category of this Frobenius X triangulated category. Yes, so that's somehow the plan. And of course, well, if we claim that we have categorifications, we need a decategorification map, so which is given by cluster characters. So, well, this is the well-known cluster character for a Frobenius category, and it actually induces, in some sense, a variant of a cluster character defined on the derived category itself. I will explain this in the second part of the lecture. And well, this generalizes to the Higgs categorification setup. We have a cluster character here, which induces, in some sense, a cluster character at the localized level, at the level of this relative cluster category, which generalizes the bounded derived category. Okay, are there questions or remarks so far? No. Okay. Yes. Then let me. Then in the rest of the lecture, I would like to explain this diagram, and then next time I will come to the construction of the Higgs category and the relative cluster category. Okay. So this localized version is new even in the Frobenius case, and it is crucial, for example, in the categorification of quasi-cluster isomorphisms. For example, the DT transformation, when defined as a cluster transformation, is an example of a quasi-cluster isomorphism. And the quasi-cluster isomorphisms also arise when we mutate at frozen vertices. So it's certainly an interesting notion. And we would like to understand it categorically. So this is what I will do in the second half of the lecture. But now this is the plan for essentially for the rest of the 3 lectures. Okay, yes, so today I hope I will be able to finish this first section. Then I will come to a class of examples, which is very useful because it allows us to see both at the same time, the Frobenius picture and the Higgs picture. So these is in this case, the Frobenius category will just be the category of modules over a pre-projective algebra of Dynkin type. Then I will go to the general setting and define the relative derived category in the Higgs category. And finally, I will look at the effect of mutations, both at frozen and at non-frozen vertices, and categorify the notion of quasi-cluster isomorphism in the general case. Well, general under the finiteness assumption relative Jacobi finiteness. Okay. Then, okay, so let us look at the localized cluster character in the Frobenius case. So as before, we have our ice quiver Q. We have the cluster algebra with non-invertible coefficients associated with it. Yes, so here is a very simple example. We take this ice quiver. Then the cluster algebra with non-invertible coefficients can be described as this quotient defined by the unique exchange relation. And then we take K-linear-Goldschmidt-Frobenius category such that the stable category is Hom finite and 2 Calabi-Yau. So the dual, this is the dual over the ground field. The dual of Hom in the stable category from X to Y should be canonically isomorphic to Hom from Y to the second suspension of X. This is the suspension or shift functor. This is the Calabi-Yau property, this cell duality formula. And now we assume that our category E contains a basic cluster tilting object. So it decomposes, we're in a Kroll-Schmidt category. So our basic cluster tilting object uniquely decomposes into indecomposable summands. We number them so that the first n are non-projective and the last m minus n are projective injective. And then we assume that we're in a situation where the ice quiver, the quiver of the endomorphism algebra makes sense. Yes, so I don't assume here I don't need to assume that my Frobenius category itself is Hom finite. This works in general. It works as long as the quiver makes sense. Yes, so the quiver makes sense if the endomorphism algebra is finite dimensional, or more generally, if it is, for example, pseudo-compact, then we have a well-defined quiver. And then we want to define the cluster character, the CC map. Okay, well, for each object of E, since this is a cluster tilting object, for each object of E, we can find a conflation of this type where T prime and T double prime are direct factors of direct sums of finitely many copies of T. And then we define the index with respect to T of our object as this difference. So this difference lies in the split Grothendieck group of this additive category, the category of all direct factors of finite direct sums of copies of T. And this Grothendieck group, yes, thanks to the Kroll-Schmidt property, this Grothendieck group is isomorphic to Zn, yes, the ith basis vector of Z to the nth is sent to the class of Ti. So the first n coordinates correspond to non-projective injective summands, and the last m minus n coordinates correspond to projective, injective, direct summands. And then we define the cluster character. So we write X, well, X underlined, this is the usual abbreviation for the monomial in the xi's whose exponents are given by these coordinates. So this is the leading factor given by this index which categorifies the G vector. And then we have this expression which is the F polynomial, yes, with a certain exponent here. And the important thing is, of course, this Euler characteristic of the quiver Grassmannian of this module over the endomorphism algebra of T. Yes, notice that this, well, this is a module over the endomorphism algebra of T, and this module is killed by the idempotence corresponding to the projective injective factors. So it lives over the first n vertices, and its submodules have dimension vectors given by n components. Okay, and then one can show that this is a cluster character. So this was shown in the case where E is Hom finite in a paper with Jensen-King-Su a long time ago. And recently we have revisited it with Sadiq Bakshi, and we have generalized and simplified the argument. So one can show that this is a cluster character. So it only depends on the isomorphism class of a given object, which is clear. The cluster character of a direct sum is the product of the two cluster characters associated to the factors. And then we have the generalized exchange rule, generalized exchange relation. Which is this rule: if we have two objects, X and Y, which have one-dimensional extension space, well, if it is one-dimensional in one direction, it's also one-dimensional in the other direction by the two-color property. And then we can express the product as the sum of, well, two monomials, if you like, and the monomials are given by the middle terms of the two conflations of any two non-split conflations with n terms X and Y. Yes, thanks to this hypothesis, we have a small choice of such conflations, and all the conflations have the same middle terms up to isomorphism, and these are what we use here. And this generalizes the exchange relation. Okay, and then thanks to these properties, yes, maybe one word on the proof. Yes, so the proof is really simple. We can deduce it from the corresponding result for the stable category, using only the fact that the function which sends an object to the ith component of the index, where I is a frozen vertex, this function is additive on conflations. Once one realizes this factor, it is easy to prove. Okay, and now, well, then thanks to these properties, we get decategorification from the Frobenius category to the cluster algebra. So that n, remember, n is the number of non-frozen vertices. We have the regular tree Tn, and then by iterated mutation possible thanks to Iyama-Yoshino, we can associate a cluster tilting object with each vertex of this n regular tree. And we assume that the quivers of the endomorphism algebras do not have loops. which is the case in large classes of examples. And then by combining the results with Fu with results obtained with Giovanni Cerulli, Daniel Labardine, and Pierre Plamondon, we get that the map taking an object of E to its cluster character induces bijections between the reachable, rigid, indecomposables, yes, those which occur as direct facts of such objects, to the cluster variables, and from reachable basic cluster tilting objects, yes, these are precisely these, we get a bijection to the clusters of the cluster algebra. And then we say that we have a Frobenius categorification of our cluster algebra, yes, sorry, with non-invertible coefficients. Okay, are there questions or remarks? Yes, this is essentially a reminder. Okay, yes. And now, well, let's look at an example. Let's take let's call lambda the preprojective algebra of type A2. Yes, so it's the path algebra of this quiver modulo radical squared 0. Then we have the modular category, has a very small Frobenius category. This is its Auslander rating quiver. Yes, we have these two non-projective objects, and we have two projective objects, and well, we have two Auslander rating sequences. We have, for example, well, we have two cluster tilting objects. The sum of these three is one of them, and the sum of these three is the other. We have the exchange conflations, which appear in the exchange sequences, and these exchange conflations yield the unique exchange relation. Okay, and, yeah, and one can see that the theorem is true in this example. Yes, we get the required bijections. Okay, and so we have, in this way, we have categorified the cluster algebra with non-invertible coefficients. And so the question is, how should we categorify such fractions? Yes, fractions where we allow coefficients in the denominators. And the idea is to use the derived category. Okay, so remember, when we have a Frobenius category, we have a canonical exact sequence of triangulated categories like this, where this is the homotopy category of projective injective objects. This is the derived category, this is the stable category. And so the idea is that this sequence should be the categorical lift of this sequence. Yes, so this sequence where we pass from non-invertible coefficients by localization to invertible coefficients, and then by specialization to no coefficients at all. And yes, so the claim is that we can complete this diagram. Yes, here we have the cluster character which I have just constructed. Here we have the cluster character associated with this triangulated category and the same cluster tilting object. And I claim that I can complete this diagram in such a way and construct something at the level of the derived category with values in this ring. And okay, so here is the proposition. We can find a unique localized cluster character defined on the derived category, such that this diagram commutes, and we have the following properties. So if we have a bounded complex of projectives, then we can very easily compute its image. It only depends on the class of this object in the Grothendieck group of our category. So this is the split Grothendieck group of P, which is also the usual Grothendieck group of the bounded homotopy category of projectives. So we have a well-defined class, and this class defines a monomial in the frozen variables. Yes. So the image of P is just this monomial in the frozen variables determined by the class in the Grothendieck category. Yes. So this is one normalization condition which we need to impose, and then we need to impose that when we have a triangle in our derived category with a projective, with an object, a complex with projective injective components, then, well, we can compute the cluster character as localized, localized. The localized character at the middle term can be computed as the product of this cluster character with the cluster character of M. Okay, so we have these two conditions, and then it is not very hard to show that there is a unique such map which works. And then let's look at an example. Okay, so we continue the example, this very simple example where we take for our Frobenius category the category of modules over the preprojective algebra. Okay, so if we shift the projective module by 1 degree to the left, then its class in the Grothendieck group changes sign, and so we get 1 over P1, the inverse of the coefficient associated with P1. And if we want to compute it's the localized cluster character. If we want to compute the localized character of the simple S1 shifted by 1 degree, I claim that we get X2 divided by P2. And that is because we have this triangle. Yes, we have this triangle comes from the exact we have an exact sequence S1 P2 S2. It has an associated triangle S1 shifted by 1. And if we turn this triangle, if we rotate this triangle once, then we get this triangle. And now we can apply the second axiom, and we find that indeed should be equal, the localized cluster character of this object should be equal to the localized cluster character of this object times the localized cluster character of this object, and that's exactly what we have here. Okay, and so we can we can in fact compute we can form a commutative square. And so here we have the shift functor at the level of the derived category. We always have a well-defined shift functor, and this well-defined shift functor at the level of the cluster algebra will correspond to a certain automorphism sigma, small sigma. Yes. So this small sigma is categorified by the capital sigma, and you can describe capital sigma in this way. And then you can easily check that it is a quasi-cluster morphism in the sense of Fraser. So the shift of the derived category categorifies this quasi-cluster automorphism of the cluster algebra with coefficients, and this is well, it is just a very simple instance of the Donaldson-Thomas transformation, or maybe the simplest, one of the simplest possible examples of a Donaldson-Thomas transformation. So in general, when the Donaldson-Thomas transformation is a well-defined cluster transformation, it will correspond to the shift in the derived category, and it will be well, it will be a quasi-cluster automorphism corresponding to the shift in the derived category. And yes, and I think this is all I wanted to say for today. So thank you very much.
Thank you very much for this beautiful lecture, Bernhard.
Thank you.
Are there any questions? Maybe we'll, yeah, I think Sarah is moderating in the room, and if you have a question online, maybe just unmute yourself and ask the question or write it in the chat.
Excuse me, did you already explain the reason why this category named Frobenius and Higgs?
I'm not sure I understood the question. I mean, for the moment, I have not defined the Higgs category. I have only said where it is in the landscape. Yes.
Okay.
No. So for the moment, I have only looked at Frobenius categorifications, and yes.
Why
yes.
this is called the Frobenius?
So the part on the Higgs category was just an announcement.
Okay. Thank you.
And I will, but I will define it next time. Yes.
Relationship between the group of autoequivalences of the derived category and the quasi-cluster morphisms in general?
Let's see. Well, if you, yes, I mean, if you take an autoequivalence, it should, so we have an autoequivalence of dB of E, and we need to require that it takes dB of P to itself. And maybe this is automatic, but it's not completely clear to me that it actually is. So if we require that, let me see, then we have a chance of getting an induced morphism. I mean, then we might or might not get a quasi-cluster automorphism. I mean, in the definition of quasi-cluster automorphism, there is a condition of reachability. So it will not work for arbitrary automorphisms, but well, it has to take the cluster tilting object to an object which is reachable. And so if these conditions are satisfied, then yes, I think then it should induce. So these automorphisms of DBE of the derived category, yes, should correspond to quasi-cluster automorphisms. Yes.
Great, thank you.
Yeah, I have a small question. Why Higgs? Why the name?
Why the name Higgs? Yes. Yes. So the basic example of a Higgs category is the category of modules of the pre-projective algebra. And module of the pre-projective algebra is just the non-commutative version of a Higgs bundle on a curve. So yes, so that's where it comes from. So it is related. So it comes from the terminology of Higgs bundle.
Here, so sorry, which is the which is the potential for your third example that you mentioned at the beginning of your talk?
The potential for the third example.
The one that is not obvious.
The one where the potential probably doesn't exist, you mean?
Yeah, right.
Yes. It is the alternating sum of the three cycles. And I mean that's the canonical potential in that case. That's the potential which is given by, for example, Jensen-King. Well, if Jensen-King-Su's categorification, yes, but that gives an infinite dimensional relative Jacobian algebra.
Thank you.
Mm-hmm. And then there's a question in the chat from Xiaofa Chen. Does the passage from the Higgs category to the relative cluster category have a general construction? No. Actually, it goes the opposite way. One first constructs the relative cluster category in a rather straightforward manner, and then one constructs the Higgs category as a certain subcategory of the relative cluster category. Yes. So it's not it's not something like a derived category. It is an ambient category inside which we construct the Higgs category. I don't know. Is the chat visible in the room at the Newton Institute?
No, it isn't.
It isn't. So the question was, does the passage from the Higgs category to the relative cluster category have a general construction for X-triangulated categories, like the one from the exact category to the derived category? And the answer is most probably no, and yes.
Oh, great. Now we have a visual of the room. That's nice. Okay, are there any more questions? Okay, that doesn't seem to be the case. So let's thank Bernhard again.
Thank you very much.
That's great. And then we'll meet back next week, but 1 hour later. The Zoom link changes and it's on researchseminar.org. And I will also try to send around an email. Okay. Thanks, Bernhard.
Thank you.